Good afternoon, everyone. Welcome back from lunch. Always enjoy this time slot. I'll begin by thanking my hardworking co-authors at Cornell University and USGS. I stand up front again, as always, as the good-looking and lighthearted frontman. We are grateful to the numerous agencies and universities that took part in this research, especially the vessel crews and biologists who worked some rather long nights, often on short notice, to get the field work accomplished. When working with wind-powered drones, I've come to learn there is uncertainty when they will arrive at a rendezvous point, and therefore I was very grateful for the grace that our partners gave us. This work I'll share today was published in 2024 in the Canadian Journal of Fisheries and Aquatic Sciences. It's available through open access, so find me at a break and I'll be sure that you can get a copy. Surveying fish to estimate their abundance comes with some rather cool challenges. First, they live in water, where they can be largely invisible to the eye, especially at night, it seems. And they're also mobile. Second, they can and do react to disturbances, say from sound and light. It follows that if a fish can detect a motorized vessel during a survey, they could choose to avoid the vessel and possibly bias our survey results low. In the Great Lakes, as elsewhere, we regularly do surveys to enumerate pelagic fish using what is called fisheries acoustic methods. That is, sound waves are used to detect the fish, which makes them visible to us. Echoes from fish return off the sound waves back to the transducer, and from those echoes, we're able to estimate the fish's size and its depth in the water column. We've long had to assume that the motorized vessels collect unbiased data because we simply didn't have the tools to test this underlying assumption. With this study, we sought to answer the questions, are Great Lakes prey fish acoustic surveys unbiased? Going in, we knew from the literature that vessel avoidance by fish had been documented in marine studies. The images to the right show a stationary buoy's measure of the acoustic return as a vessel approaches and then moves past the buoy. The vertical black lines is the closest point at which a motorized vessel approached that buoy. So you can see that as the vessel approached the buoy, that the fish dove in response to the approaching motorized vessel. However, note these fish in this marine study are not the same species found in the Great Lakes, so it was unclear to us if our fishes would exhibit the same response. This diving reaction demonstrated by these marine fishes here is presumably related to radiated noise from the engines of the vessels. To address this research question, we decided we needed a silent platform capable of collecting mobile acoustic data. We searched what was available in the marketplace and chose a company called Saildrone, which is a company based out of California. In this photo, a Saildrone appears behind some rather distinguished-looking gentlemen that were all about 6 feet tall. There's 5 of them. If I had been their basketball coach putting together the program for a Friday night game, I would have listed them at 6 feet or more, maybe Russ Strock at 6'4". But if I were the coach, definitely the guy, maybe Josh, I'd have him be my point guard. Okay, so they are smaller than research vessel, but they are big enough to carry a range of sampling equipment, including a scientific-grade echo sounder with a miniature transducer. Sail drones are propelled by wind. You can see their big sail there, and they use solar cells, which you can see, to charge the batteries to power the navigation and the scientific equipment. The experiments were accomplished by deploying 2 sail drones in Lake Superior between August and October of 2022. The drones were moved into different jurisdictions to interact with the different agency vessels. The participating agencies included the Red Cliff and Grand Portage bands of Lake Superior Chippewa, the Wisconsin DNR, the Minnesota DNR, and USGS, of course. Here's an example of, we tried to get work done up in Canada with the OMRF vessel, but they were very busy at the time, so we weren't able to accomplish that. In total, we ran 44 overtakes, shown with the dots on the map. Here's an example of one overtake run south of the Sleeping Giant, which is my favorite place on Lake Superior. At the onset of night, a sail drone was sent on a predetermined transect, and the vessel milled behind the vessel, waiting for the transect to be finished by the sail drone. And when the drone had traversed 2 kilometers, the ship followed the drone path at a faster rate of speed, eventually overtaking the drone. We then could compare the transect that was collected first by the sail drone and then immediately followed by that by the ship. Another interesting facet of this study is we partnered with Michigan Tech University to conduct what are called vessel noise profiles. The graph on the right shows noise profiles on the 5 vessels we tested on Lake Superior. The frequency of the noise is on the x-axis and the magnitude is on the y-axis. And there's a dashed line on all of the graphs, which is the suggested noise levels proposed by the International Council of the Seas, or ICES, on the levels that the vessels should be in order to collect acoustic data free from vessel noise. All the crewed vessels we tested exceeded the recommended noise thresholds for the acoustic surveys at some frequencies, but none of the vessels were outrageously noisy. Unsurprisingly, advance here. That was not true for sail drone, which is shown in the bottom panel with the orange box around it. Here, the noise sail drone produces was well below the levels recommended by ICES. The low-level noise these drones do produce are thought to be come from the motors being turned on and off during navigation of those drones. Here's an example echogram collected by sail drone as an overtake occurred. On the x-axis is distance, and on the y-axis is water column depth. You can see fish present above the lake bed and also fish in the surface waters. At the point of the overtake is on the far right of the echogram. What you see near the right-hand side is a phenomenon called crosstalk. It happens because the ship's echo sounder was communicating or in close proximity to the sail drone echo sounder, so we're actually seeing the echoes from the ship there. So we removed those with bad data regions shown in green. To determine if the vessel is disturbing the fish, we are looking for evidence of changes in the characteristics of those fish echoes as the 2 platforms get close. And I'm not seeing that in this example. To test if fish avoidance, to test if fish avoided vessels, we use 4 metrics that I'll share over the next set of slides. First, we examine the acoustic backscatter, which is an analog to fish biomass in the beam. This metric is abbreviated SA and is equal to the amount of energy from fish echoes averaged over all the pings in the sample volume. For each overtake, we calculated the delta SA, which was the difference between the ship SA and the sail drone sounder SA. So we're looking at the differences measured by the 2 platforms. The unit of measure was decimals, or dB. We also measured the average depth of the targets in the beams, presuming that fish attempting to avoid the vessels may change their depth by diving, as seen in the marine literature. The time when an echo returns is converted to depth based on the speed of sound in water. We especially look for differences just before and during the overtakes to look at the depths of the fish in the water column and how they may be influenced by the vessel. We also examined target strengths, which is the strength of the returning echoes from individual targets detected in the beam. If fish avoid the vessels, we might expect them to dive in the water column. And if a fish were to dive in the water column, we would expect its target strength to decline because the target strength is proportional to the cross-sectional area of the swim bladder. And that's going to be largest when a fish is positioned, dorsal ventral in the water column. Diving lowers the cross-sectional area of the swim bladder and therefore the target strength. Lastly, we also calculated the density of fish using a method called echo-integration. We estimated density by dividing the backscatter, which is all the echoes from all the fish, by the average target strength, which is the average size fish. So you're just scaling the backscatter to figure out what the density was. We compared the absolute density, but we didn't really like that because the drones, sometimes there was a lot of variation in densities across space. So we ended up landing on using the proportional difference, which was useful because we sometimes detected, again, relatively few fish at some of our overtakes. So we looked at proportional differences in density between the platforms. And Dan, I know what you're thinking here. Let's cut to the chase. This is a very busy plot, and the guy who reviewed my talk didn't think I should use it, but I put it up here all the same. This plot shows differences between the ships and the sail drone. On the y-axis is the water column depth, 5 to 20, 20 to 40. So as you get deeper in the water column, we're moving down on the y-axis. And the 4 panels are the 4 metrics that we're testing. Each point here represents an overtake event in which we had a total of 44. Our stat analysis showed that the differences between the vessels were not significant, so we can do away with them and focus on the results of all the vessels together or pooled and comparing that to the sail drone. The leftmost panel is the delta of acoustic backscatter of the ships and the sail drones. The sail drones measured slightly higher acoustic backscatter levels than the ship. If they were the same, the box whisker plots would center on 0 or no difference. So you can see they're slightly over to the right of the 0. The second panel from the left shows the delta in target depth. That was also a push. There was no differences between the mean depths of fish detected by the motorized vessels and the sail drones. The third panel has the target strength data. Like with backscattering levels, the target strengths were ever so slightly higher in the sail drone data. So when we scaled the backscatter by the target strengths and compared relative densities in fish in the rightmost panel, we see slightly higher densities were measured by the sail drone. When we considered all of the overtakes and all of the vessels, this difference averaged about 15%. Also, there were no differences in relative density across the 5 motorized vehicles tested. Overall, these results point to very small differences between the crewed vessels and the uncrewed surface vessels, and said differently, I see no reason to be concerned about comparing past ship results across these 5 vessels, nor would I be concerned extending a time series initially developed with ships by employing sail drones into the future. We're getting near the end here. We also calculated what are called z-scores, which is a measure of how many standard deviations a given data point is above or below a mean. We fitted GAMs, or general additive models, of z-scores to the distance between the ship and the sail drone. So on the x-axis is distance. We have the 4 depth layers again. No, we have ships in columns, and then the 4 depth layers, 5 to 20, 20 to 40, 40 to 60, and greater than 60 meters in the rows. Only 3 relationships out of the possible 20 combinations here of different vessels and depth columns were significantly fitted with the GAM, but we didn't see any consistent patterns suggesting these 3 differences were really by chance alone. Twice the mean depth increased at the time of the overtake, so the fish are increasing here in these 2 panels here in the 40 to 60 meter layer, and in one of the greater than 60 meters we actually saw the fish depth decrease, but for the vast majority of that, there was no significant fit with the GAM models. It is possible that the small differences that we observed between the ships and sail drone of 15% may be tied to fish being more apt to move laterally away from the front of ships right as the ship reaches those fish. This design in the sail drones didn't allow us to explicitly test that, but that could be one reason why we might see this small difference between the platforms. That's it, folks. With that, I'll gladly take questions.